We see we push EAX there. Eventually, going back, we're left with EAX and a pointer to that there. We push that onto the stack, and then load some other stuff up. Here we have the user we're interested in is 5 for the system user. So we load into EAX the effective address of the base pointer plus OX1C, and then we write 5 to that value, push EAX, push 7, move into EAX the value of, the address of the function we want to call. That's actually in the Oracle executable itself, and then we call it. Now, I got this address by disassembling the authentication procedures essentially, and looked at what it did and thought, well, actually, wait a minute, we can hook into that and basically, manipulate the password hashes. So once we call EAX, essentially, we should have a pointer back to the user structure for the system user. We then make some modifications to that. So OXC2 bytes into the structure, we get the beginning of the password hash. So this here is the password hash. And that's the password hash for the system user when it has a password of secret like that. So we then write that into, we overwrite the extant password hash essentially there. The vector I'm using here happens to require that the exploit be written in ASCII, so this needs a bit of explanation. The exploit I'm going to be demoing, because it has to be ASCII, I've written an ASCII, what is this? A decoder, I've written the decoder writer in ASCII. So the exploit, when it begins, has the decoder writer, a buffer, a destination for the decoder when it gets written out, and the encoded exploit. So when the decoder writer executes down this way, it starts writing the decoder out this way. So eventually, the two join. And when the two join, execution continues from down here onwards. Whoops. And obviously, the decoder, all that does basically, it loops decoding this stuff here. And eventually, the decoder finishes, and we continue execution from there onwards, kind of thing. So that way we can get our arbitrary code across without having to worry about, there being like characters greater than 7F, OX7F kind of thing. Okay, the decoder itself, essentially when I encode the exploit, I take a byte of exploit, split it into 2, the most significant 4 bytes and the least significant 4, not bytes, most significant 4 bits and least significant 4 bits, add 41 to each half essentially, OX41 to each half, and then that becomes our encoded exploit. So decoding that exploit is the same in reverse. Essentially, we set ESI and EDI to point to the beginning of the encoded exploit, move the byte into the AL register, subtract 41 from it, shift it left 4 bits, and then increment the pointer to the next byte in the list, add that to the AL register, subtract 41, and eventually we're left with our original byte of real exploit code, our actual exploit code in AL, which is then written to ESI. We increment the pointers and keep on going, and until we come across this either a Q or more. So it's, that essentially is our equivalent of our null terminator, but it's not a null terminator. It's if it's Q or more, stop looping. So otherwise, go back and loop up to there. So because these slides will be available offline, before doing the demo, I've obviously got some screenshots, which I'm obviously going to do this live, but for those people who aren't going to be here, there should have been another slide in there. I must have deleted it. We can see here, we'll be logging on as manager. That works. Connecting as secret fails. You're no longer connected to Oracle. Now I've redacted the actual vulnerable function itself for those people who will be reading it later, because it's better to go that way, because I don't want to be handing out real live exploits. And afterwards, we try and log on with our old password. It doesn't work anymore, but we log on as secret. So demonstrating this. Now, you guys are obviously going to get to see it because I can hardly redact it in front of you. But if we connect Scott/Tiger, if I show you here, if I connect system/manager, we're connected. If I obviously try as connect with secret, invalid username or password. So if I now, this is the actual code. Let me walk you through this. So essentially what we're doing here is filling up the buffer here. X is our buffer, essentially. We overwrite the save return address. Well, actually, we're overwriting the exception handler here, to be honest. I should fix that. And we're overwriting it with this value. This value exists in oracle.dll. There is a pop-pop-ret at this address. This here is obviously the ASCII equivalent of it there. Some more bytes. Oh, we have to have a short jump up here. Basically, this jumps us over the address, basically, when we're in memory. We need to adjust ESP correctly for this to work. And this here is our ASCII armored shellcode decoder. This here is the buffer where it all gets written to. So that's where our decoder is written to. And this here is the encoded backdoor. Funnily enough, it starts with jail. It's like, don't use this, otherwise you will go to jail. That's just completely coincidental. And here is the termination. This could be Q, for example, or more. And then we execute the function. Now, because this actually itself calls terminate thread on the thread itself to continue to continue execution. It's going to hang in this window. So it's hanging now, but this should have changed the password hash to secret. So if I go one up there and hit enter, I'm now connected. So all that's done is basically, as I said, called an Oracle function that's returned a handle to the user structure for the system user. We've overwritten his password hash in the SGA with the known hash for that which would equate to secret and gain access. So the idea there is obviously in terms of detection, runtime patching we can detect quite easily because we can hook calls to, for example, say virtual protect X or virtual protect. So if anyone tries to do any runtime patching of code, because code is loaded as read-only, if we don't have code which is code pages which are writable, then we're going to have to call this. And by default, they're not writable. So if we hook this and make sure the call is coming from known safe locations and so on, then if someone exploits a buffer overflow to call virtual protect X or virtual protect, then we can monitor accesses for that and so on. And again, changes to the import address table. They're quite easy to spot too. It's easy relative to the problem of changing data. Changes to data that are supposed to be changed, for example, the password hash of the system user. Well, sure, we can go ahead and protect that area of memory, watch it for changes and everything like that, and alert if there are any changes and say we may have been compromised. Well, what about the next thing? You know, we can't go around protecting every bit of data that has some relevance to the security of the server, because eventually we'll be using up so much processing time that there'll be no processing time left to service database queries. So this is a real problem. How do we protect against this? Well, if someone can come up with a solution, a light solution for that, then that would be wonderful, and you could probably make millions of pounds from it, or euros rather. Currently, I think the best thing you can do is keep your servers locked down and watch for abnormal activity. So, any questions? No?
We have still 10 minutes for questions.
Sure. Sure.
What is Oracle doing about it right now?
Well, there's nothing wrong with this. I mean, at the end of the day, once you're running code through a buffer overflow, for example, then you're running code at the end of the day. It's not like you can do anything to protect against these things. Or if you do own the server with sys privileges, you know, it's like, well, you can do anything you want anyway. So it's not really an Oracle problem, to be honest. Once you've got the keys to the kingdom, you've got the keys to the kingdom, you know. So in terms of protecting against things like new flaws as and when they come up, well, they're taking steps to remediate new buffer overflows or SQL injection flaws all the time. So. But it's not, Oracle's done nothing wrong here, by the way, nor if this was applicable to SQL Server or Postgres or MySQL, no database vendor is at fault here. It's just simply, once you own it, here's stuff you can do to retain access at a later date kind of thing. So, no other questions? Sure.
When the real admin then logs in again, next time, you change it to secret and then revert it back to the old.
Yeah, well, we could repeat the exercise and change it back to, the old password hash, essentially.
And then you have two processes hanging there? Or?
Well, no, it's not. It's no longer hanging. This is on. This SQL Plus is hanging on my machine, the attacker's machine kind of thing. And as far as the remote server's concerned, the thread's just terminated kind of thing. So as far as it's concerned, the client's disconnected kind of thing, and that thread's torn down. So, yeah, it's just SQL Plus doesn't recognize that the thread's terminated on the remote server. It thinks it's still there kind of thing. And it's waiting for a response coming back.
Since you changed it in memory, if it's rebooted, the old password reverts.
Correct.
So if you're sneaky users,
Could you repeat the question so it's in the audio?
Well, the thing was, have you got the mic there?
Yeah. I was just saying that since it's only changed in memory, if the system's rebooted, it reverts, and then if you're clever, you just change the password, log in, and change it right back.
Absolutely.
And the only way you're saying you'd notice any of that is if you're hooked one system call that you're using.
Sure, we could hook this function and everything like that and make sure it's coming from a verifiable source, for example. But at the end of the day, we can we can modify something else that has security relevance. For example, we could change the fact that it's the bits that say whether you're a DBA or not. For example, we flip a 0 to a 1 or a 1 to a 0, whichever happens to be. So we protect against that, and we protect against this, and eventually we've got this whole long list of things we protect against. And as I said, you can't really do that with a database server, because for every 1,000 things you think of protecting, there's going to be another 3,000 which you're not protecting, and we can still use it has the same equivalence kind of thing of achieving the same thing. But yeah, I mean, once the server's stopped, and we would need to reinfect it again, obviously. So it obviously would have to depend on the target environment, whether they apply patches or not. If they don't apply patches, then your initial vector, reinfection vector, is still going to be there kind of thing. So, no other questions? Great.
Well, in that case,